So last time we have computed the number of microstate for an ideal gas, and we have found this result that the entropy, which is the k times the logarithm of the number of microstate, is nk times log of v plus 3/2 nk times log. Well, let me write it in terms of the temperature. Log squared. Okay, where I've used the fact that the energy for an ideal gas is equal to n 3/2 nkt, okay, which we have derived, and I have expressed the entropy as a function of temperature, okay, because then we have analyzed this experiment where we have taken two systems in equilibrium at the same temperature and with a number of particles N1 and V1, N2 and V2, but with the same density. Okay? So in both cases, N1, V1 is equal to N2 divided by V2. Okay? And then we have done this experiment where we have removed the wall, and then we have put the wall again, and then we have a different system. Okay. Now, if the molecules of the gas in system 1 and in system 2 are different, then this is an irreversible transformation, because in this stage the particle will mix, and when you put back the wall between the two systems, you will have a different macroscopic system. Okay, and this is an irreversible transformation, and then the change in the entropy is just given by the change in the entropy between this system and this system. You see, the temperature does not change, so this part will not change. And but what will change is that here you will have the entropy of the final system. The final system will have total number of particles, which is N1 plus N2 log V1 plus V2. And the entropy of the initial system is N1 K log V1 minus N2 log K log V2. So that you can write these as N1K log sorry, with a minus sign. Okay, so the entropy is positive. The change in entropy is positive. Okay. So, and this is called the entropy of mixing. Now, however, if the two systems are the same gas, the same molecules, then effectively this change is a reversible change, because there is no way in which you can tell the difference between this state and this state. If the density is constant, here there will be approximately N1 particles, the volume is V1, and here there will be approximately N2 particles and the volume is V2, because the densities are the same, okay? So then this is a reversible change, and the delta S should be 0, okay? So so this is called Gibbs paradox, okay? So how to solve this paradox? Well, the idea is that if you think about it, when you have the same gas in both these two systems, here the number of different configurations which you can get at this stage is one of N1 plus N2 choose N1, okay? So there are these many ways in which you can get a different arrangement of the particles in system 1 and system 2. Is this right? Okay. This is the combinatorial factor, okay? Then, indeed, what this means is that when I compute the number of microstates which describe this system here, then I should consider the product of the two of the number of microstates in system 1 and the number of microstates in system 2. Yeah?
I don't understand. When you say that there is no change of state and when we put the wall back, why is that? Because if they are not the same gas, they are not.
No, if there is if the gas is different, the two parts, then the final state is different. But if the gas is the same, then the final state will be the same, right?
Yes, so we are talking about one kind of gas.
Yes, now we are talking about one kind of gas, and we are trying to understand how we can solve this paradox. Because if you use the formula, this formula here, then you would just get the entropy of mixing after this transformation, okay? And so what I want to argue is that there are this many number of microstates which are consistent, which are equivalent, okay? Which are equivalent with a system where these two states are in equilibrium, these two subsystems are in equilibrium at the same temperature, at the same density, okay? So, indeed, when you compute the number of microstates of the whole system, you should consider the product of how many microstates can the system 1 be times how many, the number of microstates in which the system 2 can be, and then you should multiply by this factor, okay? You should multiply by n divided by, I choose n1, okay? Where n is equal to n1 plus n2. Now, if you rewrite this, this is n factorial times omega 1 divided by n1 factorial times omega 2 divided by n2 factorial, right? And now you see that if I define my number of microstates of the total system as this one divided by n factorial, then this has the nice property that it will be proportional to omega 1 times n1 factorial. So it will be proportional to the same way of counting the states of the microstate for the system 1 and the system 2. Okay? So this sounds like a mathematical trick, but it's actually deeper than that. It is actually telling you that you cannot, if the particles are indistinguishable, if the particles are the same, you cannot distinguish between microstate where particles are interchanged among themselves. Okay? You have to count the number of particles, the number of microstates in such a way that you are not distinguishing between different arrangement of the particles. Okay? And you see, if you have this property, when you compute the entropy of the total system will be just the entropy of the sum of the two systems. Okay? If you compute the entropy of the total system, this is k times the log of this omega 0, and this will be just the sum of the log of omega tilde 1 and omega tilde 2, which is the sum of the two entropies. So the change in the entropy in this case will be exactly equal to 0. Okay? So the change in the entropy when you go from this state to this state will be equal to 0, as it should. Of course, if the two gas are different, this is not true. Okay? This is not true because the two, indeed, if the two gas are different, this number will depend on the number of particles of type 1 and the number of particles of type 2 separately. Okay? So I will not have this n factorial, and indeed the correct number of counting the states will be just omega 1 divided by n1 factorial, omega 2 divided by n2 factorial, and I will have again the entropy of mixing. Okay? Yes, please. Sorry? Yes, so if we use different particles, we have an irreversible process. Okay? But if the particles are the same, and so if we use if here and here there are different particles, then this is an irreversible process, and we should have a positive change in the entropy. Okay? If instead the particles are of the same type, is the same gas, then this is a reversible process, and the change in the entropy should be 0. Okay? So this formula here does not give you this result when the particles are the same, of the same type. Okay? The way to correct it is to is to use a different way of counting the number of microstate, which is the number of microstate as we have computed divided by n factorial. Okay? Okay, so if you do this, then the entropy has an additional term. if you now define the entropy in this way, then there is an additional term which you have to add to this formula, which is minus the log of n factorial, right? Times k. Okay? And so you see, this is using Stirling approximation. This is n log n minus n. So this minus k times n log n, I can put it together with this. So I have nk times log v over n plus nk times 5 over 2 plus 3/2 log of 2 pi m kt divided by h squared. Okay? So now you see that this entropy as a function of n, v, and t is really an extensive quantity. Okay? Because if I change n into a times n and v, morning, a times v, and the temperature remains the same because it's an intensive quantity, then you see that under this transformation, v divided by n remains v divided by n. Temperature does not change, and you just get that this is, you get that the entropy of a system which is a times bigger is just equal to a times the entropy of the initial system. Okay? Are there questions? Is this clear? Okay. So, so why do we need to do this to count the number of microstates in this way? So we have seen that when we count the number, we have to define the entropy as k times the log, the number of microstates as n, v, and e divided by n factorial. So why this n factorial? So this n factorial actually comes because in classical mechanics we can actually, when we solve a mechanical system, we describe the system with the coordinates and the momenta, and we label each of the coordinates and the momenta by a label of the particle. So in classical mechanics, we can think of following each of the particles, and so we can think of labeling each of the particles. Okay? But in quantum mechanics, we cannot. You know that in quantum mechanics, the wave function must be either symmetric or anti-symmetric with respect to exchange of the particles. So we cannot put a label on the particles. Okay? So this n factorial is a way to say correct for this inadequacy of classical mechanics. Okay. However, it's an approximate way. It's an approximate manner. Okay. Because indeed, if you really have a quantum system, then in a quantum system you will have energy levels. And your system will have n A particles in level A. And of course, you should have the sum over all the levels of NA should be equal to n. Now, if the particles are really indistinguishable, it means that not only I cannot even distinguish between states where I interchange any particle which is in the same state. Okay, so if I interchange, so not only I cannot, so I have to. I mean, the number of the correct number of counting the states. In the correct number of counting the states, I should divide by the number of ways in which I can distribute the particles in the states. Okay. So indeed, in the correct way of computing the number of particles, instead of n factorial, you should actually put n, the combinatorial factor, the multinomial factor, which counts the number of ways in which you can distribute all the particles in the energy levels. Okay. Now, this we are going to discuss. What will be the effect of this factor here in later lectures. But let me just point out when do we expect that this way of computing, counting the states will be correct? Okay, when is it that this a recipe which is based on classical mechanics will work? Okay, and essentially it will work if as long as the number of particles, I mean this NA factorial is essentially 1. Okay, so if you have that this product of A of NA factorial is 1, which means that NA factorial is essentially 1. And this means that NA is either 0 or 1, because you know that 0 factorial is equal to 0 and 1 factorial is equal to 1. Okay. Then if the occupation number is always less than 1, then this way of counting the states will be approximately correct. And this will occur when the expected number of expected number of particles in each state is much less than 1. So when does this occurs in a real in an ideal gas? Okay, so let's try to understand what are the physical conditions under which this thing occurs. Yep.
I mean, mathematically it's correct to say if NA factorial is 1, then NA is equal to 0 is acceptable. But what does it mean? I mean,
Sorry?
NA is equal to 0. We have
There is no particle in that state.
So,
Yes. So when we have computed this number here, you remember we have computed all the possible states. We have to compute all the possible states in which we can distribute n particles in these states. Okay, you remember our states? We did this plot where we had this vector n, say, of the occupation number of the states. And what we said is that the possible states are all those. So this is a very high dimensional space. So it has 3n dimensions. Okay. So and all the points on this surface is a possible state of our system. Okay. Yeah. Yes. A represents yes yes, in our case, you have a collection number quantum numbers. Okay. So but for any set of this collection of quantum number, you will have a number of particles with that with those quantum numbers. Okay. And what we are saying is that the number of particles in each quantum state should be small.
And big N is the number, is that the number of particles?
Large n is the number of particles. And NA is the number of particles in state in level A. Okay, because I'm considering an ideal gas. Okay, so particles are independent. So the energy is the sum of the energies. And the way I construct a state of the system is just by putting different particles on different single particle states. And each particle can be in a different state. Okay. Yeah. No. Yes, that is exactly the point. Okay, so this formula here will occur when the occupation number of the states of our system is typically very small. Okay, so when the number of particles in each energy level is very, very small. Okay. So this will be in each microstate this will be a different number. Okay, if you take for each microstate you will have a different set of these numbers. Okay, so you can think of boxes. Okay, so the boxes are the energy levels, and then you have to distribute the particles. Okay, so the boxes are the energy levels, and each of these boxes is as a label A is an energy level, and it has its energy. And then there will be a number of particles in each of these energy levels. So this will have Na equal to 1, 1, 0, 1, etc., etc. Okay? Okay? So now for a certain gas at a certain energy E or a certain temperature T with a certain density, so how many particles will I find in each of these energy levels? So in order to compute this, one way to compute this is to say, well, this the number of states, I have to compute how many boxes will I have, and divide, if I want to know, if I want to compute this number here, this will be the number of particles divided by the number of boxes. Okay? And the number of boxes is the number of accessible energy level at a certain energy E. Okay? Or let's say at a certain energy or below a certain energy E. Okay? So how many are the boxes? So we see that essentially the total number of states, the total number of single particle states is essentially all those so the so the number of states are all those which are inside typically a sphere of radius two m v to the 2/3 times the energy E divided by h. Okay. So the total number of states will be essentially this for a particle will be the cube of this. Okay. An estimate of this will be essentially R cube. Okay, which is proportional to V divided by h cube times E to the to the 3/2. So it's essentially proportional to volume times temperature to the power 3/2. Okay, so you see that the average occupation number will be proportional to n divided by V times T to the 3/2. So when the density, so the classical, this means that this condition will be fulfilled when the density is very, very small, or when the temperature is very, very high. Okay, so the classical way of counting the states, which is given by this formula here, will be correct for low densities and high temperatures. Whereas if you are if you go to low temperatures and if you go to high densities, you will start seeing quantum effects. You will start seeing effects which are related to the fact that you are not counting properly the number of states. Okay, and we are going to discuss this. But so this is just to give you a sense of the fact that this classical statistical mechanics, typically for ideal gases, holds for low densities and high temperatures. Okay? Okay, if there are no questions, then we change subject. Questions? Yeah?
I understand how most of the states cannot be occupied with the particles when it's low density. But when we have high temperature...
When we have high temperature, you should think that this sphere gets larger and larger. So the number of points which are on the sphere also increases very much. Okay, and then because the temperature is, the energy is proportional to the temperature. Okay, so yeah, exactly, yes. So you need the radius of the sphere increases with the energy and with the volume, right? So that the larger is the volume at fixed then, the larger is the volume and the larger is the energy, and the lower is the occupation number of each quantum state. No? Okay. Okay, so what I would like to do now is to, so what we have said is that we derive thermodynamics by establishing a correspondence between a macro state, which is specified in terms of, for example, macroscopic variables, and microstate. And now I would like to make this connection more precise. More precise, in particular, more precise and more general. And the way to make this connection more precise is to introduce the concept of ensembles. Okay, in order to introduce this concept, so let us focus on classical systems. Okay, we have a classical system, so there is an Hamiltonian. So the microstate will correspond to a collection of coordinates and a collection of momenta. So there are 3 coordinates and 3 momenta for each particle, so there are 6n coordinates, 3n coordinates and 3n momenta, okay? And I will call these just Q and P for simplicity. Now it is very useful to think of microstate will be essentially specification of all these numbers, And it is very useful to think about this as a point in a space, okay? And this space is called the phase space. And is the space of all coordinates and momenta, okay? So this is a 6 n-dimensional space. And each point in this space is a complete specification, microscopic specification of a classical system. Okay? Okay, so each microstate you can think of, we would like to associate microstates with points in this space. Okay. Now, what do these points do? As time goes on, they move. Okay. They will follow a certain trajectory. And this trajectory, at each point, will have a certain velocity, which is given by q dot and p dot. Okay, the time derivative of coordinates and the time derivative of momenta. And what are those two things? So q dot is d h dp, and p dot is minus dh dq. These are so the velocity in phase space is given by so this is true for each of the coordinates, right? Okay. So this gives you the dynamics of the system. Now, what is the idea? Imagine that you want to do an experiment. You want to measure something. Okay, you have a function, and what you want to measure will be a function of, in general, coordinates and momenta. Okay. For example, you want to measure the energy. The energy will be a function of coordinates and momenta, or the I don't know, some other physical quantity. Then the measure of this, typically if you do an experiment, you should think that you will essentially probe your system for a certain time. And what you actually can think you would measure in your experimental apparatus is some sort of time average of this quantity as the system moves in phase space. Okay. So you could also think, I mean, if you do a certain number of measurement, you could also think of doing different measurement at different times and taking the average. Okay, so this will be sort of something like this. Okay, if we want, of course we could think of computing this value by solving all these equations and making this integral, but it is clearly hopeless because not only because we have to solve a very large number of differential equations, but also because we don't know the initial conditions. Okay, so it's really hopeless. So another idea is that of instead using the concept of ensembles, so that as the system moves around in phase space, it visits many points, and all these points, now you can think of taking, instead of, and essentially what you want to do is to make averages over all these points, okay? So now what you can think of doing is to say, well, let us take a very large number of copies of the system that will be in different points of the space, and each of them will have its own dynamics. Okay? So you imagine, like, instead of following just one system, you imagine having a very, very large number of identical systems, and which move according to these equations. They will generally be systems with different initial conditions. And so what you can think of, and this is the concept of ensemble, okay? So an ensemble is a collection of many, many points in the phase space, okay? Now, in order to be more precise, you want to define how many. So for any volume, typically this phase space is called gamma. For any volume in gamma around a particular point Q and P, which is given by which is given by a small neighborhood. You take a particular point Q, P of this thing, of where of volume dq times dp. So you want to have in your ensemble a number of points in each infinitesimal volume, which is essentially proportional to the frequency with which the system will pass in that volume. Okay? So you want to define this object as 1 over t times the limit as the time goes to infinity of the, so 1 over t should be here, of, let me call this is the time spent, so the time spent in delta gamma by the system. So imagine that I can follow my system in phase space, and I can compute how much time, in a long time interval t, how much time does it spend of this long time interval t, how much time does it spend in this particular volume. Okay? Then I can compute this limit. And generally, this limit will be proportional to the size of the volume. Okay? So I define through this limit an object which is the density. Okay? Okay, so the idea is, if I can think of a distribution of points such that the density of these points is such that it is equal to the frequency around each point in phase space, is equal to the frequency with which my system passes close to that point, then you see that by using, I can turn all these time average in averages over this density. Okay? By definition, it will be, by the definition of how I define this, density, I can turn time averages into averages over this density. Okay? And essentially, this will be exact if I take the limit t going to infinity. Okay? If I, sorry? Yes, this will be normalized, right? Because the total time spent in all the phase space will be equal to t. Okay, so this will have, as you say, right, as you point out, rightly, this should have the property that the integral on all the phase space, rho of q and p, should be equal to 1. Okay? This is the integral over all the phase space. So these are 3n dimensional integral and another 3n dimensional integral, right? Okay. And this is a function which depends on 6n on all these coordinates. Okay. So this idea of ensembles is it's just a trick which I use to turn time averages into averages over this density. So now my problem is no more, I don't need to integrate all these equation of motions, provided I can compute this, this density here. Okay. Still, this is a very complicated problem because this is a function of 6n variables. Okay. Very good. So this is a small volume in the phase space. Is the number of so this is the fraction of points of my ensemble. Let me write. This is the fraction of points of the ensemble in the volume dq dp. Okay? So I'm taking this small volume in the phase space, and I want that in my ensemble there is a fraction of point in this in each volume, which is equal to the fraction of time that my system passes through that volume. Okay. Because if I define my ensemble in this way, then I can compute averages in this way. Okay. Very good. Yeah. Sorry? Yes, this is going to be the probability density that to find the system in this microstate. Okay, you know we are going to see that in order to define microstate, we cannot really think of points as microstate. We'll have to think about small volumes as corresponding to a microstate. But I'll come to that. Okay. Okay, so now let us consider a particular system, in particular an isolated system. An isolated system will have an energy which is constant, is a constant of the motion. And so since the energy is constant, then the part of the volume which is visited by the system will be finite. The region of the system which is visited by of the phase space which is visited by the system will be finite. Okay, because the momenta cannot go to infinity. I mean, because the Hamiltonian generally will be well, it's p squared over 2m, so it's an increasing function of p. So if the energy is bounded, then momenta should be bounded, and also the coordinates will be constrained in a given volume. Okay, so if I'm studying a system of particles in a volume V, then each of the coordinates q will be in that volume. Okay, so this means that this integral for all practical purposes will be on a finite portion of the phase space. And in particular, this portion of the phase space will be the surface where the energy is constant. Okay, for an isolated system, the surface of constant energy, but the Hamiltonian is constant, will define the part of the phase space which is visited. Okay, so well, notice also that so if the system is subject to an external force, so if there is an external field which varies in time, then also the energy will change in time, and as a result of this, also the density will also depend in time. So this thing will be different from zero if there is a time-dependent say force acting on the system. Okay. But if there is no time-dependent force acting to the system, then just the system will have its own energy, and it will just move on points of the same energy. And what we want to do now is to study this motion, okay, quite in general. Okay. So. So let us consider a small volume, and let's say there is a fraction delta gamma of points of my ensemble in this volume. So how will this number change in time? Well, the change in time of this delta gamma will be essentially the change in time of the density, right? Q, P, and T. And I'm allowing also for time dependence, okay? And this integral should be on the volume, let me call it dq. On this, say, small volume let me call it delta omega. So I call delta omega this volume of phase space, and delta gamma is the fraction of points of my ensemble which are in this phase space. So this is just how the number of points of my ensemble will change in time, the definition. And why will they change in time? Because some point which is inside this volume will go out, and some point which is outside this volume will go in. Okay? Because all these points are moving with a certain velocity v, which is equal to this. Okay? So the change in this well, it can be can be computed by taking an integral over all the boundary of this region delta omega over the surface, I'm calling sigma the surface of this volume. Yep.
Is it the rate of change of T gamma or T omega? T delta omega?
So this is the volume,
Yeah.
okay? The region in phase space, and this is the fraction of points in this phase space of the ensemble, the fraction of systems.
So yeah, why we some?
So this is so if I take this density and I integrate over the omega, then you get the fraction of points of the ensemble in this volume here, right? And I'm interested in the change of this. Okay. Now say this number will change because some of the points which are inside go out, and some of the points which are which are outside go in. Okay. And in order to compute this thing, I have to compute how many points are on sigma, and the rate at which they are going to go out is proportional to the product between the normal to sigma and the velocity. Okay. So this will be the integral over the sigma times on the surface times the density on the surface times the normal velocity n times the velocity. Okay. And this velocity is just q dot and p dot, which is given by that. And of course, say you see when the n when the velocity has a positive component on the normal, then the points will go out. And when the velocity and the normal are on opposite direction, there will be an increase in the number of points. So there is a minus sign here. Okay. And I can use Gauss theorem to evaluate this. This will be equal to the integral on the volume of dq dp times the divergence of rho times the velocity. So if I compare these two equations, what I see is that the dynamics, I mean, how this, how the density changes in time has to satisfy the continuity equation, which is the rho dt is equal to or plus the divergence of rho times b should be equal to 0. Okay? This is just a statement that in my ensemble, no point is created and no point is destroyed. Okay? I'm just following a number of points as they move in this space, but I'm not destroying any point and I'm not creating any point. Okay? So for any small volume, the change in the number of points inside the volume is just given by those who enter and exit. Okay? And this is the continuity equation. So what is the divergence of, what is this divergence here? So this divergence is a divergence computed over all the coordinates, right? So if I write it explicitly, this is the sum from I equal 1 to 3n of the derivative with respect to qi of rho times the component of the velocity on qi, which is qi dot, plus the derivative with respect to pi of rho times p dot I. Okay? Now, let us do this derivative. This is sum I from 1 to 3n of d rho d qi times q dot I plus d rho d pi q dot p dot I, and then I have rho, which multiplies d q dot dqi plus d p dot I dpi. Okay? So what are these two terms? So this term here is just, you see, is the change in rho as you move on the trajectory. Okay? So it's just it's just the total derivative of rho with respect to the t, of rho computed in q of t, p of t, and t, if you want, minus the derivative of rho with respect to t. Okay? So if you want to compute the total derivative of rho as a function of t, what you have to do is to take the partial derivative of rho with respect to coordinates and then the time derivative of the coordinates, right? and then the explicit derivative over time, the partial derivative over time. So this part here is exactly equal to this. Okay. And what is this part here? Well, here you notice that dq dot I, dpi, dqi is equal to the second derivative of the Hamiltonian, right? And dpi dot dpi is equal to also minus the second derivative. Okay? So if the Hamiltonian is an analytic function of the coordinates and these two derivatives are the same, so this term is exactly equal to 0. Okay? So you see that now if you plug this result here, what you get is a quite important result, which is known as Liouville theorem. Which states that the total derivative of the density over the trajectories, the total derivative of the density with respect to time is equal to 0. So if you sit on a particular system and you follow the trajectory, you will see that on the trajectory the density does not change. Okay? So this is very, very important because what it tells you is that rho is a constant of the motion. Rho is a constant of motion. Okay? So if this is so, then you can think that rho must be a function of the constant of the motion. Okay? And in this case, essentially, it tells you that, in particular, if the constant of the motion is just the energy, then rho must be a function of the energy. Okay? You see that this is very, very important. It's very, very important because we have turned the problem of determining a function of 6n variables into the problem of just finding a function of one variable. Okay? Which is how does this thing depends on the energy. Okay? And this is really a big, big step. The other thing which you get from this Liouville theorem is that if you look, you remember we had this hypothesis of a priori equiprobability of microstates. This essentially tells you that all the states which are visited by the dynamics are equiprobable. So the probability is the same. Okay? So this is very important because it gives you some foundation for this a priori equiprobability of microstates. Of course, it does not really prove that you can really consider that all the states which have a certain energy will have the same probability. This is because it might be that states with different energies, because the dynamics does not visit all the states with that energy. Okay, so in general, so if this is your phase space, then there will be so the states with a given energy will be say be a surface in this space, okay? But this surface might be disconnected, okay? So if you start from your system on one particular part, you may never visit this other part, okay? So in this sense, what the dynamics will do is to have to sample uniformly all the states here and never sample the states here, okay? And so what is the surface? So imagine that you really have an ideal gas, okay? So in the ideal gas, we have, well, the Hamiltonian is just sum over I from 1 to 3n p squared over 2n. Okay? What is the trajectory of the system in phase space of this of the ideal gas? Huh? Is a sphere? So imagine that your system is your ideal gas at a certain point is here, in this point. Where will it move?
Now we need the energy to be constant, right?
Yes.
So
No, I mean, just take this equation here. Okay, so the equations are that Q dot I is equal to is equal to P I divided by M, usual thing, and P I dot is equal to 0. So, so as far as the P is concerned, the point does not move at all. Does not move at all in this direction. Actually, you have to consider the real gas. The real gas is in a box. Okay, so if there is a particle which moves with a certain momentum p, it will hit the wall and then go back. Okay, so actually, so if your system is in this point here, then with a certain momentum p, then it will jump to a point which is down here. Okay, and actually, what you have is that when it is here, it will move with negative velocity, so it will follow a trajectory which is which is essentially like this. Okay. This is just for one particle. Okay. For one particle, you will go from imagine that this particle is moving horizontally, and this is L, it would go from minus L over 2 to L over 2. Okay. So this is the phase space of one particle, in case of one particle which is sampled by your system. And the system will just jump from here to here, okay? And then if you imagine you take another particle, then, well, it will go on another point. But this system will not sample the space of all possible momenta and coordinates which are accessible, okay? In general, I mean. So you need to, in particular, say, you can think of a system where all the particles move just horizontally, back and forth. It will have a certain energy, and it will just continue staying in this state without exploring anything else. So, I mean, these hypotheses that you visit all the states which are consistent with a certain energy, it's really an important hypothesis. It's called the Ergodic Hypothesis. Okay. And in the case of a gas, I mean, this is interesting because what you really need is that the motion of this particle is somewhat disordered. Okay, so already if you take one particle, well, if you take one particle which is exactly moving horizontally, then it will do like this. Okay, but if you take one particle which is moving with a certain angle, then at least you can think that then it will bunch, and so it will explore the whole volume. And maybe if you look at the coordinates of the system, the momenta of the system along the two axes, so it will also explore the whole P space. Okay. If you think at more particles, then you have to assume that particles will also collide one with the other. When they will collide elastically, the energy will be conserved, and they exchange momenta. And so, so indeed, the motion of the point in phase space will be very, very complicated. In the case of, say, of this elastic collision, trajectories will not be continuous, okay? Because you always jump from a state with a certain momentum to a state with a different momentum, right? So the motion is a bit different, and the fact that you really sample all the states with a given energy is non-trivial, okay? But we will assume that. We will assume that this is true. And so this is called the Ergodic Hypothesis. So let me write it down just. So the Ergodic Hypothesis states that all states with HQP equal to E are visited. So there are cases where, and it's very difficult to show that this hypothesis is verified in a specific system. And there are cases where essentially physics is in very good agreement with this hypothesis. There are cases where instead the fact that this hypothesis does not hold is really physically important, and this is the case of phase transitions. In phase transition, what you have is that your phase space gets broken into different parts, which are related by symmetry. So the simple case is a magnet. A magnet can be magnetized either in one direction or in the other. And if it is magnetized in one direction, it will stay magnetized in that direction. It means that even though there are states with the same energy with the other direction of the magnetization, the system will never visit those states. Okay? So this is a case where the ergodic hypothesis clearly does not hold, and there is what one calls ergodicity breaking, in the sense that the fact that this hypothesis does not hold is a breakdown of this ergodicity hypothesis, which is that all states with same energy are visited. Okay. So this is a good place to stop, and I hope you have received the lecture notes. Did you? Okay. Questions? What is the ergodic limit? So the ergodic, I don't know what is the ergodic limit, but the ergodic hypothesis is what I wrote here. So no, let's say what I've been saying is that what we will do in the following is to work as if this hypothesis is satisfied. Okay? In the sense that we will do this next time. What from this equation, this you see, this equation tells you that all the states which are visited and which have all the states which are visited have the same density. Okay, and we know that all the states which are visited have the same energy. Okay, but it is not true that all the states which have the same energy are visited. You see? There might be states with the same energy which are not visited by the system. Okay? And then when we take averages over these, assuming that all states with the same energy are visited, we will get a result which is different from when we do time averages. Okay? So all the states which are visited have the same density if the energy is constant. Okay? And all the states which are visited have the same energy. Okay? But it is not true that all the states with the same energy are visited. There might be some state, in my plot here, if the state with a certain energy, is disconnected, for example, there are two, if you look at the points in the phase space where this is true, there are, for example, two surfaces, then if you start with your point here, then you are you will get stuck here, and if you start with your point here, you will get stuck here. If you do time averages, you will get a different result if you are here or if you are here. Okay, take the example of a magnet. Okay, the example of a ferromagnet, polarized, is when it is when you have a ferromagnet with a magnetic moment in one direction, you are only sampling states with the magnetic moment in that direction, right? But there are other states with the magnetic moment in the opposite direction, in another direction, which have the same energy. You're never going to visit those states. Okay? So if you take if you take the hypothesis that whenever two states have the same energy, they have the same density, then you are going to have a problem. Okay? This is the case where these are the cases where this ergodic hypothesis does not hold. If you want, the ergodic hypothesis tells you that you know that all the states with the same, which are visited, have the same energy. The ergodic hypothesis tells you that the converse is also true. All the states with the same energy are visited. Okay? It cannot be. You can have examples like the ferromagnet where this is not true. Okay? So it's important to be aware of this. Okay? Yeah. We said that the number of points of the ensemble is proportional to the volume, right? And so what is the question?
This is a definition, or is it what? Is it an assumption?
Yes, this is a definition. It's a definition of the density. You define the density as the density of points of your ensemble in a particular point QP as the frequency with which the system visits that point. Okay?
Then you concluded that if we average over time,
Yes.
over these volumes are the same.
Yes. This is not clear? It's not clear? So this is so you just write that, well, you want to do the limit as time goes to infinity of 1 over t integral t0 plus t f of q of t p of t. Now this is the time average, right? Now what I can do is to write this integral in this form. The integral in dq dp of f of q and p times the limit as t goes to infinity of 1 over t times the integral dt t0 and t0 plus t. And here what I do is I put a function which gives me 1 whenever p of t is equal to p and q of t is equal to q. Okay, so this is the delta function. Okay, is a 3n dimensional delta function. Okay, so this is precisely well. What I'm doing here is for densities. Okay, so if you do it for a small volume, then this will be the indicator function of the volume. Okay, but this is precisely what I describe by this. If you want dw of t divided by dq dp. Okay, so the frequency with which I visit the point qp. Okay, is this clear? It is a bit more clear than before. So in order to do this integral, what I can do is to say I compute the fraction. This is essentially how frequently I visit the point Q and P. This is an integral which essentially gives me 1 whenever I'm in Q and in P. Okay, so this is the fraction of time that I am in Q and P. And then I average this over all possible values of Q and P. So, and this is my definition of rho of Q and P. Okay. So it's just I sit on each point Q and P, and I compute the frequency with which the system passes by. Okay. And this is this is the way with which we go from one to the other. Is it more clear now? So there is another thing I wanted to tell you. I mean, geometrically, what just a moment. What this tells you is that if you follow a system, a trajectory, then the density will be constant. So this tells you that the trajectories of the system, if you take two systems and they follow two trajectories, these trajectories will never coalesce. So trajectories will never coalesce, because if they did, then the density would increase. Okay? So this means the trajectories do not coalesce. Okay? So they always stay separated. Okay? A question? There was another question?
This is exactly that's is it related to what we do in experiments, like averaging over time and taking many particles in such experiments?
Sorry?
Is this one related to doing an experiment on one system for a long time and doing on many systems at the same time?
Yes, so I want to define this ensemble, a set of many systems, such that when I average over these many systems, over this ensemble, I get the same result as if I average over one system over time. You see? So these ensembles are defined precisely in this way. Okay? And the whole thing is that you turn the problem of having to solve all the differential equations into a problem of having to compute just the density function. Okay? No, and so is this clear? The concept of ensembles. I mean, you can think of say a physical way of thinking this ensemble is you have your system which moves in phase space, and every 3 years you take a point. You wait 5,000 years and you have a collection of points. Okay, and so you take a point every time interval delta t. Okay, if you do this, you follow just one system. At the end, you will get a collection of points. This is an ensemble. Then you can think of let's follow this system in time, and let's see how this cloud of points in the phase space moves. And this cloud of points is described by this as a density, which should be described by this this function here, this density function. Okay. So is this clear that if you construct the ensemble in this way, then time averages are the same as averages over the ensemble? Yes. So this is the way in which you construct this ensemble. So you take one system and you pick one copy of your system every, say, every day, for example. No? And then you look for an infinite number of days, you will have an infinite number of copies of your system. Imagine that the system is always in the same conditions of energy, number of particles, and volume. Okay. And then it is clear that now if you average over these points, it will be the same as averaging over time, right? Okay.
Apart of the fact that the assumption of ergodic theorem,
Yeah.
is there any other contradiction between time average and ensemble average?
No, this is the only problem, no, which you can have. The problem is that not all the points with the same energy are visited. No, the dynamics does not access all the points. Otherwise, if the hypothesis is true, then this Newville theorem tells you that all the points are visited equiprobably with the same probability. So you have a reason to really believe that this equiprobable assumption is right. Okay. Yeah. Okay, so see you on Monday.